Okay, so last time we discussed polar form of complex numbers, and then we derived the Euler's formula. So today we are going to further explore Euler's formula, and we will derive some trigonometric identities. So I'll go with this plan. First, we'll compare the graphs of e to the x, e to the minus x, and e to the ix, and e to the minus ix. So we'll see how these graphs look like. You already know how the graphs of these functions look like. So for this purpose, we'll be using Mathematica. And then after this, we'll try to build a connection between the Euler formula, unit circle, simple harmonic motion, and uniform circular motion. And we will briefly describe the unitary time evolution in quantum mechanics because its form is very much closely related with the Euler's formula. And finally, we'll derive some of the trigonometric identities. So let's begin with this part of the lecture. Well, we'll graph these functions. So let's get straight into Mathematica and see how these graphs will look like. From the basic physics or calculus, you're already familiar that this is an exponentially growing function and this is an exponentially decaying function. But just for the sake of completeness, let's see how these graphs look like. So this is a small Mathematica code. The first line here will plot me exponential x and exponential minus x. These two plots on the same axis, and the range of the x values will be from -2 to 2. So let's run this cell. So from here, this red graph is for e to the ix, e to the x, sorry, for the exponentially growing function. And the blue one is for exponential minus x, or e to the minus x. This one is called exponential growth function, and this one is called exponentially decaying function. And note one thing which is very crucial, even for negative inputs, if x is even if x is negative, the output of the function or the y values are all positive. So exponential function, whether the value of the x is plus or minus, it will always return a positive value, as can be seen from this plot. So this one is the graph of e to the x, and this one is the graph of e to the minus x. This one is exponential growth, this one is exponential decay, and you may be already familiar with this one. For example, the charging of a capacitor, or the current in an RLC circuit, and so on. Similarly, the decay of some electromagnetic, the decay of a certain nuclei, and so on. So they are modeled by this exponential curve. So this was about these e to the x and e to the minus x function. Now, by using a similar technique, we will try to plot e to the ix or e to the I theta, one and the same thing if theta is real. So whether I plot e to the I theta or e to the ix, it will be just one and the same thing. So in the second cell, I'll be trying to plot e to the I theta in the complex plane, where x-axis will be the real part of the complex number and y-axis will be the imaginary part. So let's run this cell and see what we will be getting. I'll tell you what's going on. So this is the plot of e to the I theta for very few inputs. For example, in the first, in this table, if I'm putting theta equals 0, then e to the I theta is 1. If I gave theta equal pi by 2, then this will be 0 and this will be 1, and I'll get iota. If theta is pi, then I'll get -1. If theta is 3 pi by 2, I'll get minus iota, and if theta is 2 pi, I'll get 1. So 0, for 0, I'm getting 1, for 2 pi, I'm getting 1, and this is actually this point, this one. So this is 1 point, but it's actually 2 points, because this is 0, 1, as well as 2 pi, 1 point. Then this point is where the value of the theta is pi by 2. And this is the point where the value of the theta is pi. This is -1. And this is the point where the theta is 3 pi by 2. And finally, this is 0.2 pi. So I have given only 4 or 5 inputs to this function, and this is the graph. So this axis, this is the real axis, or the real part, and this y is the imaginary part, or the imaginary part of e to the I theta, and I'll be plotting these complex numbers. These are complex number. This is a complex number. This is complex. So these are four complex numbers. These two are only real, and these two are only imaginary. So let's give this function more inputs and see, okay, how can how will this change. So let me, for example, move this to some higher inputs. Now in this table I have like 7 or 8 points, and these points are now coming. These new points are coming from these new values of theta. This point, this point, this point, and this, and these four were the old points. Now let's increase the number of points in the table and see, okay, what will happen. So let's increase more and see. I guess I have plotted quite a lot of points. So it's 200. No, I was aiming for 20. So let's see here. So look, we are kind of going towards a circle in this complex plane. And let's increase these points further, and let's try to make it look more like a circle. So this is finally the plot of e to the I theta, and this is a circle. This circle is called a unit circle because the radius of this circle is 1, as can be seen from this plot, 1 everywhere. So the radius of this is 1, and it's called a unit circle. So the plot of e to the I theta is a circle in the complex plane. So this is one take-home lesson. And let me now go back to the writing part where I want to write and explain certain things. So e to the I theta or e to the ix, where x is a real number, is a unit circle. This is what we just saw. It's a unit circle. But we know from this e to the ix formula by the Euler's equation that it's equal to cos of x plus iota sine x, where this is the real part and this is the imaginary part. And if I take a complex number, this is x and this is y, sorry. For example, I have a complex number x plus iota y, and if this is making an angle theta and this radius is r. So we know from the previous lectures that this is equal to r cos theta, and this is equal to y equal to r sine theta. So this is x and this is y. And let me quickly prove this. If I square these, like if I take this thing, x squared plus y squared, what I'll get r squared cos square theta plus r squared sine square theta. If I take r common, I'll have cos square theta plus sine square theta, and cos square theta plus sine square theta is actually 1. So I have this thing, x squared plus y squared equals r squared. So this complex number over here is actually in the polar form, this is actually equal to e r I theta. But now if I take r equals 1, what I'll get, if r is 1, I have this thing, x squared plus y squared is equal to 1 squared or simply 1. And this is a unit circle. And this actually corresponds to e to the I theta or e to the ix, one and the same thing. So this is what we just saw geometrically, and that's the analytical proof of this thing, that e to the ix is actually a unit circle in the complex plane. This is just this is what we saw. Now, if I further digest this Euler equation, this is the real part, and this is the imaginary part of this complex number, this whole complex number. So the real part, if I plot the real part, as a function of x. Suppose this is x and this is, let's suppose, a real part of e to the ix, which is actually equal to cos of x. So its plot will look something like this, the graph of a cosine function. Sorry for my bad drawing, but this is the cos of x. And similarly, if I plot this y as a function of x, or the imaginary part as a function of x, for example, this is my, oh, sorry, this is x, and this is the imaginary part of the function e to the ix, which will be equal to sine x. So this will look something like this, sine and cosine. So as a function of x, if I look at these graphs, so along the x-axis, I have oscillatory motion. Along the y-axis, I have oscillatory motion. And if we now picture the circle, oh, sorry, this is not a good circle. This is my best attempt to a circle. So if we now look at this circle and we think about it as a combination of two independent motion. For example, I have a particle and this particle is moving along this circle. So we know from the basic physics that this particle, uh, uh, even if it's moving along the circle with a constant speed, its projection along x-axis and its projection along the y-axis. This is a projection along x-axis. This is a projection along the y. If this is moving along x-axis, these projections will move along their respective axis, but these projections will perform simple harmonic motion. So this is what we know from basic physics, that if a particle is moving with uniform speed on a circle, then the projection on the x-axis and projection on the y-axis will perform simple harmonic motion, which are actually sines and cosines. So in this one function, e to the ix or e to the I theta, I have like sinusoidal function. This is cos of x for the real part and sine of x for the imaginary part. So my next plot will be, the next graphical representation will be that this time I'll try to move a point uh, over a unit circle, and I want you to see how the projection on the x-axis, on this axis, and on this axis moves or perform simple harmonic motion. So let's go to the Mathematica and see how this happens. So let's play this cell and see. So now I have this red dot, which will move with a constant speed on this unit circle, and this is a vector which has a length of 1. And this is actually a phasor, e to the I theta. Its phase will only change and its magnitude will stay constant. So let's, before running it, let's look at this moment of time when the point is here. Its projection along the x-axis is equal to cos theta, and its projection along the y-axis is this green line. This is sine theta. This is actually r cos theta. This is actually r sine theta, but r is 1 in this case because this is a unit circle and the radius is 1. So this is r cos theta, which is simply cos theta because r is 1, and this is r sine theta, so it's sine theta because r is 1. So let's now run this simulation and see how this point will move and how these their respective projections move along the x and the y axis, or the real and the imaginary axis. So this is how it works. And look at this projection along the x-axis. This is performing simple harmonic motion, going back and forth. And similarly, the vertical projection along the y-axis, this green arrow is also performing simple harmonic motion. So this is how we can visualize this function, and we can go in steps just like this, and similarly this way. So this is just to give you a connection between the Euler's formula and the simple harmonic motion on a circle, or uniform circular motion in a circle. Now next, if you recall from quantum mechanics, if you have a state, this is actually the unitary time evolution in quantum mechanics and the connection between the Euler's formula. So if you recall from quantum mechanics, if you have a state at some time 0 and you have some Hamiltonian for this system, let's suppose this is the initial state at t is equal to 0, at time 0. This is our state at time 0. This is the Hamiltonian of the system, and we want the state at time t. What will be the state at some other time? For this purpose, we are going to solve Schrodinger's equation. Partial psi by partial t is equal to h psi. And if my Hamiltonian is time independent, then I can solve this equation, and the solution will look something like this. Psi of t as a function of time will look something like e minus I h t divided by h bar, and this will be some state at t is equal to 0. So this is my state. This is the state at time t. So this is the state at time t, at t time, and this is the state at time 0. And how I'm getting this state from this is the initial state or this is the final state. How I'm getting from the initial state to the final state? I'm getting through this operator. This is called the unitary time evolution operator. And this is, if my initial time is 0, I can write the unitary operator as a y I iota h bar t divided by h cut. And this is something very, very close to this thing. Even if I have a minus sign, the minus sign would only mean that if e to the I theta is rotation in the clockwise sense, then e to the minus I theta will be a rotation in the reverse sense, in the anti-clockwise sense. And if this is anti-clockwise, this will be clockwise, and so on. So the minus sign is just only bringing this difference, and otherwise this is just a rotation. So this operator, this u e to the I theta, is called the unitary time evolution operator. Let me write it again. U of t is minus I h bar t by h cut. And what it does, it unitarily evolves, unitarily, it's a rotation operator. It rotates state. So it unitarily evolves state from some initial time, let's say 0, to some final time. Let's suppose this is the state at t equals 0. How can I go to a new state at time t? I have to rotate my state by this thing, because we saw that this thing is just a rotation, because e to the I theta is simply a rotation. But just note one thing: this is only true if we have closed quantum system, and by that I mean there is no dissipation of energy from the system. There is no friction, and there is no environmental external agencies which are taking energy out of the system. Only then the system will evolve unitarily, and the probabilities will remain conserved. So this is a crucial point to note, that this unitary evolution operator is only the state will only unitarily evolve if the system is closed and it's not losing any energy to the environment. So let's get back to the mathematical simulation and see. So if you look at this picture now in a different sense of quantum mechanics, suppose I have some initial state. My particle is, let's suppose here, it's not strictly true for quantum mechanics, because my particle cannot be exactly at one location, but just let's forget about those details and let's focus on the bigger picture. Let's suppose this is my state at time 0. This is the vector in a two-dimensional Hilbert space. Let's suppose it's a spin states qubit in a two-dimensional Hilbert space, and this is my state at t is equal to 0. What will happen to it I um, if I apply certain Hamiltonian? So if a Hamiltonian is a Hermitian operator, and then if I exponentiate the Hamiltonian as here, I'll get a unitary operator, because look, this is Hermitian. So if we exponentiate a Hermitian operator, we get a unitary operator. So this thing is unitary. And we know from basic of the linear algebra that what unitary operator does, it only rotates a vector. It cannot change its length. So a unitary evolution or unitary operator will only rotate a vector from just say from one point to the other point. So if we look at this graph from that perspective, and if I now, this is my initial state, this is psi of 0, ket 0, then if I apply a certain unitary operator, then it will rotate it from here to here. And if I apply, let's suppose, another chunk of the unitary operator for some other time, it will move it further, and so on. So it depends, okay, for how longer time I'm applying this unitary evolution operator on my state. And this is the basic idea that this is a unitary evolution. The length of this vector will remain constant because the probabilities will be conserved. This is required in a closed system for the conservation of probabilities. So the operators in a closed quantum systems are unitary operators, and they can be pictured as just rotation along um, some circle, only rotation, no stretching and shrinking, because the shrinking would mean that you are losing some probability, or there's a leakage from the system, and so on. So this is a little connection with the quantum mechanics and this Euler's formula. So this thing is similar to our a to the I theta, the Euler's formula. Similarly, formulas for this expressions like these, they occur most of the time in quantum mechanics. Similarly, in angular momentum, the angular momentum generators are also in this form, e to the I theta. So e to the I, some generator of rotation, which are usually the those rotation matrices and so on. So I'm not going to this detail, but just to tell you, there is a connection between um, the rotation and this e to the I theta with the Euler's formula. So I think this is enough for the geometrical interpretation. Let's go towards some trigonometry, and let's quickly do some very quick calculations. By the way, those are very simple calculations, but just uh, for the sake of introduction and completeness, we have to quickly go through them. So trig identities from Euler's formula. So I'll derive some trigonometric identities. For this purpose, let me quickly consider e to the ix in two different form. E to the ix is equal to cos of x plus I sine of x, and e minus x is equal to cos of x minus sine of x. I'm looking for expressing sine theta and cos theta in terms of the Euler's function. So for this purpose, I'm adding this, let's suppose 1 and this is 2. If I add 1 into, what I'll get, these two will cancel, and I'll get e to the ix plus e to the minus ix. Here I'll get 2 cos of x, and this will give me cos of x is equal to e to the ix plus e to the minus ix divided by 2. This is my expression for cos of x. And similarly, if I subtract 1 from 2, this would give me, in a similar fashion, I would get e to the ix minus e to the minus ix divided by 2 iota. And this would be my expression for, this is iota. So this is for sine x and this is for cos x. So these are the representation of sine and cos in terms of these Euler function. They'll help us later in some calculations. So just note these equations. For example, this is A, and this one is, let's suppose, B. Now I'm going to derive some basic trigonometric identity. For example, you know from your 10th or 12th grade that we can express sum of angles in terms of the product of the angles. So to prove those, consider, let's suppose I'm taking this expression, e to the I alpha plus beta. And this can be written as e to the I alpha into e to the I beta. I can write these two in this form because this alpha and beta, they are real numbers and they commute. So as long as these are real number, I can use this kind of an expression. I can use this expansion and I can write these in this form. Um, if alpha and beta were matrices and operators, then there are certain restrictions. I have to consider the commutation relation and so on. But here these alpha and beta are just real numbers, and I'm good to go with this scheme. So for this, let's use this definition of the Euler's formula. I can write this as cos alpha plus iota sine alpha. And for the second one, I can write, sorry, this is cos beta plus iota sine beta. And let's carry this side as it is for a moment. Uh, Now let's multiply these two brackets. Take this one, multiply with this, and then multiply with this. I'll get two terms. So this is cos of alpha, cos of beta plus iota, cos of alpha, sine of beta. And then take this one and multiply with this and this term by term. So I'll get two more terms. Let's continue with this color. So this is sine alpha, cos of beta, and now this one, no this one. This one has iota, and this one has iota. So if I'm multiplying these two terms, I'm multiplying two iota and two iotas, and iota square is equal to -1. So I'll get a minus sign here, and then I'll have sine alpha and sine beta. So, and let's write this as it is. Now, let's expand this side and rearrange that side. So this side can be expanded like, let me use Euler formula for this side as well. So this will become cos alpha plus beta plus iota sine alpha plus beta. And I can rearrange this side. This term has no iota, and this term has no iota as well. So let's collect these two terms. So this is cos alpha, cos beta minus sine alpha and sine beta. So this is one term. Now the other term, this term has iota, this term has iota. So I'm taking iota common, and this is actually a plus iota. And let's write this side as cos of alpha sine of beta plus sine of alpha cos of beta. Now I have an expression which is a complex expression. On this side, I have a complex number. On the other side, I have a complex number. And we know from the equality of two complex numbers from our very first lecture that if we have a complex expression, and so the condition for the equality of the complex number is that the real part of the complex number on the left-hand side must be equal to the real part of the complex number on the other side, on the right-hand side. So for this equality to hold, this side cos alpha plus beta must be equal to this term because this is the real part and this is the real part here. Similarly, the imaginary part, this side, this thing is the imaginary part, excluding this iota. Note it, iota will not be counted, and this is the imaginary part on this side. So for the equality of these two sides, this is the condition that the real parts on both sides must match and the imaginary parts on both sides must match. So equating real and imaginary parts, I can arrive at two trigonometric expression, trigonometric identities. So equating real part gives cos alpha plus beta equals cos alpha, cos beta, and this is actually a plus. No, so sorry, this is minus. So this is sine alpha and this is sine beta. This is my equation, let's suppose C, and my next expression will be for this one. So sine alpha plus beta will be cos alpha sine beta plus sine alpha, cos beta, and this is, let's suppose, my expression D. So similarly, if I write a little homework for the readers, if I take this thing, alpha minus beta, then I can write it like I alpha into minus I beta. I can use Euler formula for here, and I'll get four terms, two terms here, two terms here. Then I'll multiply this, and then I'll get four terms. And then by doing a similar process where I'll compare real and imaginary parts, so I'll get two more identities for cos alpha minus beta and sine alpha minus beta. So please complete this very quick exercise. Then for some double angle identities, I have two approaches now. Either, for example, if I consider, for example, here, if I take alpha equals beta equals theta, if suppose alpha is equal to beta, and let's call it theta, it's a third name. If they are equal, then I may label them by just one label. Let's call it theta. So if I use alpha is equal to beta equals theta, I can obtain the double angle identities from here. But let's not do that, and let's derive those from scratch. So if I reconsider this part, alpha plus beta, as e to the I alpha, e to the I beta, and let's take alpha equal beta equal theta. So this side will transform to e to the I theta plus theta, and this will become e to the I theta, this will be e to the I theta. Now this side can be written as e to the I2 theta, and this side can be written as e to the I theta whole square. So let's keep this side as it is, e to the I, sorry for the bad handwriting, e to the I2 theta. Let's expand this. Let's put the definition of Euler formula. So this is cos theta plus iota sine theta, and then there is this whole square. So let's open this by using alpha plus beta whole square. But remember, if this is my B and this is my A, so this is A, this is B, this B has this iota. So this is going to make some difference. So this is cos theta plus iota sine theta, and then this square. So let's open this by A plus iota B. Sorry, let's open this by using this expression, A square plus B square and so on. So this will be equal to cos square theta plus B square. Remember this is B, this whole is B, and this has iota. So if I square iota, I'll get a minus sign. So this will be minus sine square theta, and then plus 2 iota cos theta sine theta. Let's open this other side. So this opening this side is going to give me cos 2 theta plus iota sine 2 theta. And on the other hand, I have to write these two terms as a collection, because these are free of iota. And then I'll take this iota common, and this is 2 cos of t sine of t. Again, using the same logic, we have complex numbers on both sides, left hand side, the right hand side. The only way that the equality will hold is that the real part on this side must be equal to the real part on this side. So this will give me, comparing the real parts, is going to give me cos 2 theta equals cos square theta minus sine square theta. And similarly, comparing the imaginary part, this is the imaginary part on this side, and this is the imaginary part on this side, is going to give me another important and very famous trig identity, 2 cos of theta and sine of theta. So this is my expression. Let's suppose E, and this is F. So I have got these two other important double angle identities. And I have yet another identity, sine square theta plus cos square theta equal 1, which I can prove by using these two expressions over here. Let me go a little up. This one. This is sine theta. So if I square it, so I'll square this whole thing. And similarly, if I square this side, I'll square this. So this is a very simple exercise. So I'm sorry for this. Sorry for the interruption. There was a problem in the software. So I was discussing that sine square x plus cos square x of theta equal 1 can be proved easily. I have to use the definition e to the ix minus e to the minus x divided by 2 whole square. And for the other one, I have to use e to the ix plus e to the minus ix. This is square, this is iota, and iota square is minus 1. So if you apply, if you do a simple algebra, just apply this square here, apply this square here, and a lot of cancellation will occur here, and ultimately you'll get 1. So this way we can derive almost all of the trigonometric identity by using just this one expression, e to the x equal cos of x plus I sine of x. And just quickly, we can extend this idea further to hyperbolic function, because we know that cos hyperbolic function, cos hyperbolic x is equal to e to the x e to the minus x divided by 2, and psi hyperbolic x is equal to e to the x minus e to the minus x divided by 2. Now, let's suppose this is equation A and this is B. I can obtain these expression by using some the definitions of sine and cos. For example, sine x is equal to e to the ix. Let me begin with this one. Cos of x is equal to e to the ix plus e to the minus ix divided by 2. Let's do a change of this expression here. Let me replace x by ix on both sides. So everywhere I will replace x by ix. So this x is replaced by iota x. Let's see what happens. So this iota is here, and now I'm replacing this other by ix. Minus I is there, and I'm replacing the other one by ix. So this is going to this is cos ix. This is cos ix. I'm sorry for the interruption. I'm sorry, there's a problem with the software, and it's restarting again and again. So I was discussing that if I take, let's suppose, cos of x equal e to the ix plus e to the minus ix divided by 2, and replace x by minus x. I'm doing this replacement. Everywhere I will replace x by ix. So this is cos ix. This is ix plus minus ix divided by 2, and I square is equal to minus 1. So this is going to give me minus x plus, this is also an iota here. This will give me minus, and minus will plus. So this is plus divided by 2, and this is actually e to the x. This is plus e to the minus x divided by 2. And see what we got? Cos hyperbolic x. So cos ix is equal to cos hyperbolic x. And similarly, sine ix is equal to minus sine hyperbolic x. This can be proved by using similar approach. So this way we got these hyperbolic functions as well. And then the other can be easily obtained because the tangent hyperbolic is equal to tan hyperbolic x is actually equal to sine hyperbolic x by cosine hyperbolic x, and so on. And similarly, if we have expression of sine x in terms of e to the I x, e to the minus I x by 2, and for cos of x, e to the I x plus e to the I x by 2, we can obtain similarly for tangent, cotangent, and so on. So we can play with all these equations, and we can derive a lot of trigonometric as well as hyperbolic identities. For example, if I recall correctly, in hyperbolic function, we have something like sine hyperbolic square minus cos hyperbolic square x equals 1. And this can be proved by using these expressions. This can be derived. I'm not quite sure whether the sign is here or this is the correct expression, but there is surely a minus sign, and this is different from this thing. Sine square x plus cos square x equals 1 if we have a simple trigonometric function rather than the hyperbolic function. So there are a lot of hyperbolic identities, and they can be proved in a similar way. All we need to do, we just need to take, for example, this is sine alpha plus beta, or sine, let's suppose if we have uh, sine x and we want to go towards the hyperbolic counterpart, we just need to replace x by ix, and we'll go towards the hyperbolic part, the hyperbolic. So this will be equal to sine hyperbolic x with a negative sign, and so on. So this is it for today. And this actually shows the power of this Euler formula, that how easily can we do this trigonometry by using this Euler formula. So thank you very much.